Hello, welcome to my channel. In the previous episode, we delved into the renowned BZ reaction and explored a variation that employs ferroin exclusively as the catalyst. Today, we embark on a journey to uncover another, less prevalent variation that utilizes cerium as the catalyst. We will compare the outcomes obtained with and without cerium in this reaction. Before we dive into the BZ reaction or Belousov-Zhabotinsky reaction, let's take a moment to explore the element cerium. As the second element in the lanthanide series, cerium holds a remarkable position as one of the most abundant lanthanide elements on our planet. It's named after the dwarf planet Ceres. However, cerium and its compounds hold limited significance in amateur chemistry. Consequently, the majority of the BZ reaction demonstrations you can find on YouTube were performed without cerium.
Anyway, with that being said, that brings us to the end of the project. As I mentioned before, in the future I might try to explore some of the other variations of this reaction. There are some bubble-free ones which might be interesting, and there's also the original recipe which uses cerium ions as well.
However, it's worth noting that the original oscillating reaction, discovered by Belousov himself, utilized a cerium salt as the oxidizing agent. Cerium and its compounds are less readily available for amateur chemists. While they may be occasionally accessible, their prices tend to be quite high. The only exception is cerium dioxide, which is commonly found in ceramic supply shops. In this YouTube video, the author demonstrated the process of synthesizing diammonium cerium nitrate, sometimes called ceric ammonium nitrate, or CAN for short, using commercially available cerium dioxide. I'll provide a link to this video in the description below.
In today's video, we're going to make ceric ammonium nitrate from cerium oxide glass polishing powder. Ceric ion is a strong one-electron oxidizing agent. In terms of its redox potential, it's even stronger oxidizing agent than chlorine gas. In organic chemistry, cerium ammonium nitrate is used to oxidize many functional groups. Also, it's used in chromium etching. But I don't have any use of it, I just want to make it because it has a nice reddish orange color. In terms of chemicals, this is what I use. In the back I have 68% nitric acid, ammonium nitrate, ammonium hydroxide, and cerium oxide glass polishing powder. In the front there are sodium hydroxide, hydrochloric acid, and hydrogen peroxide.
Cerium stands as the sole lanthanide element capable of existing in solution in the +4 oxidation state. Notably, the cerium 4+ ion is one of the most potent oxidizing agents in laboratory settings, surpassing even chlorine and potassium permanganate. Now, let's explore this reaction. As a reminder, here is a list of the ingredients. To best compare the results with and without cerium, we will explore the reaction with just ferroin and the reaction with both ferroin and cerium. It's worth noting that cerium alone can be used as the catalyst for the BZ reaction. However, since cerium 4 is yellow and cerium 3 is colorless, the oscillating color change is less striking and sometimes difficult to observe through a camera. In this experiment, we will add solution A, solution B, and solution C in a 7:1 to 0.5 ratio as the previous episode. But before adding the same amount of ferroin, we will add a couple of drops of cerium 4 ions, which is solution E. On the screen, you are watching the result with just a couple of drops of cerium solution. Compared to the reaction without cerium, my first observation is that the color contrast between waves have become more pronounced, presumably due to the yellow color of the cerium 4 ions. The waves appear to be thicker as well, although in the previous runs without cerium, some waves appear to be thick too. In another run, after adding a few drops of cerium-4, the distance between the waves appear to be much farther away, resembling the waves in the ocean. And a few days later, I run this experiment again. In this time, I had to remake a new sodium bromate solution, which is solution A. After using the new solution, a different kind of wave pattern was formed. Here is a side-by-side comparison of the Ferroin-only version on the left and the cerium version on the right. One thing I've noticed is that while the Ferroin-only version, despite creating a different pattern each time, will always work as long as I try to mix all the ingredients with the same ratio in the correct order. Considering that the ingredients ratio will be slightly different for each run, the recipe without cerium, which is the Ferroin-only version, has a relatively large tolerance for the variations in the starting conditions. However, when adding cerium to the equation, we've introduced a whole new dimension of complexity into this already quite complicated system. That means, despite my best effort to maintain consistent reaction conditions, every now and then, it wouldn't form any patterns at all. This could be because I'm using a highly scientific method of measuring cerium solution by adding 2 drops each time. Yep, using drops to measure volume, that sounds very scientific. However, I believe this actually highlights the beauty of this reaction, which is essentially a chaotic system. Even a slight variation in the conditions could lead to vastly different results, including the formation of patterns or the complete absence of patterns. Similar to the Ferroin-only version, this reaction can also be performed in a beaker. Oscillating color changes would occur. In this beaker, I added 14 milliliters of solution A, 2 milliliters of solution B, and 1 milliliter of solution C. After waiting for the solution to become colorless, indicating that all bromine had been consumed, I added about 0.2 milliliter of solution E, which gave a yellow color hue due to the cerium-4 ions. Then, upon adding ferroin, which is solution D, we can observe a wide variety of color changes immediately, which is fascinating. However, over the next several minutes, the solution gradually changed color from a dark brown to red, very slowly, but no oscillation occurred. This made me a bit worried for a moment. To speed up the reaction, I turned on my heat plate. That's why you can observe some steams on the beaker. However, after a while, nothing seemed to be happening yet. Just when I was about to give up on this run, something unexpected happened. Look at this. Compared to the Ferroin-only version, the color transition of this run appeared more striking. It started with red, then turned blue, purple, and finally dark brown, which restarted the cycle. The color change oscillated every 40 seconds or so, even though I had turned on the heat plate. This was a significant difference from the 23 seconds of oscillation time observed in the Ferroin-only version at room temperature on a winter day. Since I had left the heat plate on, you can see that the color changes become more frequent over time. Let's examine the color transition in slow motion. We witnessed a wide range of colors during this transition. For the rest of the video, I'll play it at twice the normal speed. That concludes my video for today. Thank you for watching this video. If this video has intrigued you, or you learned something new today, please remember to like, subscribe, share, and comment so I can make more videos like this. See you next time.